אבל הוא הבונה.
Sitting here in advance of the
Everybody's counting hands. Yeah. Okay. So we have one more talk before lunch, and Ofer Feinerman from the Weizmann Institute of Science will talk to us about the ant colony post-precision society.
Okay. Yeah, so the title is a post-transition society, but actually I'm not signing this part. I'm not sure what that transition is exactly, or post or pre. But whatever it is, I'm not going to describe the transitions and stuff too much. Just try to give a picture a little bit of the structure of an ant society or some ant societies that we know in the lab. And maybe the main thing that I'll push in this talk, or main idea, is this notion of individuality. And again, it's not the notion maybe that we talked about. The individual I talk about is this single insect. And this will be the hero of our talk. So these are the ants as they were 150 million years ago, before this transition, solitary insects. And now 150 million years have passed. You see, not much has changed. We still have the same structure, same three parts, these wings, same 6 legs. They turned black from these stripes, but they moved underground. Something is very similar, right? It's 150 million years. Something is very similar, right? There seems to be some constraint on the system. And I think it's important. I think that one has to not to forget this when we look at the ant colony. Okay, so let's look what changes have been made and what's special in ants. So I'm just going to give a few examples. Nothing here is conclusive. So one, of course, is this reproductive decision of labor. This is why we call it a post-transition. I call it a post-transition society. So you see the queens and the sterile workers, and here are the eggs. But of course, there are many, 15,000 species of ants, and many different kinds of colony structures. Okay, so you can have this, maybe you can call it the classical structure, a single queen, maybe singly mated, and many sterile workers. But you can have, so that are all sisters, quite closely related, but you can have also other structures where you have multiple queens, multiply mated, and when you look for the relations between the different workers, you see almost zero relationship. And you have other strange things like the ants we'll show later, where talking about Paul yesterday, that the females and the males are 2 different species. There's no gene transfer between them at all. And the only connection between them is the sterile workers. So you have many different, and you have also colonies that all ants can reproduce. Many different structures. All of them have similar behaviors, I should say. But is it post-transition, pre-transition? I leave it to people understand better. Okay, so there's this differentiation. There is, of course, caste differentiation also in ants. You know, the dogs that differentiated very quickly into all these types, and the same of course in the ant colony. There's differentiation. So there was more of it in the larger colony. So these are the leafcutter ants from South America, and there's huge differentiations into castes, and they're kind of also sitting on. So you see the queen, the nominated queen, and then you have these castes, the warriors, the workers, and these castes also kind of sit on the production line of the agricultural endeavor of these ants. They engage in the fungus growing, and you need to cut the fungus into finer and finer shreds. And of course, this caste differentiation reminds us of what we see in a multicellular organism. And I just want to say that this fact that we call a superorganism a superorganism is first because it's made of many organisms, of course. But second, again, it's an evidence thing that say that you have all these structures and all these analogies that rise that seem to be similar between an organism and the superorganism. One of them is the differentiation, and there are many other examples. I won't go into them, into the whole debate of whether superorganism is a good or bad word. Then we have another adaptation. This is the social stomach. So ants and bees, probably wasps also, develop this social stomach. It sits on top of the. It sits before the regular stomach where they digest, and this is a place where they can store food and then regurgitate it and pass it on to other ants. So it's a really social stomach characteristic organ that developed in the ants. And in the lab, actually, we film these interactions. So you can see here we look inside the ants like with fluorescent, like we X-ray, see what you ate today. You cannot, they cannot lie to us. They had the extra cookie or something, like I had 3 in this coffee break. So this one had 3 cookies, this one had only 1, and we can actually visualize through them and see how the food transfer occurs between the ants. You can see this transfer that, yeah. Slowly you see this one getting more full. So cool. This one is drinking the. So this is the social stomach. So clearly an adaptation for social living. And then there's even a social stomach caste, not in all ants, but these are called the honeypot ants from southern United States. There's really a caste it's like just a sitting social stomach or an ant refrigerator, if you may. And they just keep the food. They grow to be cherry sized even. And I didn't taste them, but I wish I will one day, despite being a vegan. And then maybe one of the more interesting organs to look at is the brain. What happens to the brain? So I think slowly I'm going to focus, and the talk will kind of focus in this direction. What happened to the brain? What happens to the brain in the social living and social insects in particular? So what would we expect? So one, you can say we have this social brain hypothesis that Liz brought up 2 days ago. So when you live in a society, you have a lot of communication, you have to understand the others, etc. You have to grow larger brains. So perhaps ants have a larger brain. You expect them to have larger brains than their ancestors or than other solitary insects. Or there's also other opposing hypothesis. The group living actually gives you smaller brains, right? If you think of the expensive brain hypothesis, so you wanted to hold the least brain as possible, not to waste energy. And perhaps we have this thing called this notion of collective cognition that people talk about. So perhaps if you have collective cognition, you can kind of release the need to hold the large brains. So this, again, is just a hypothesis, and together with James Tranello, we played with a very simple toy model of this, where we could just show that if navigation capabilities increase non-linearly with brain size, then sometimes it's good to have many ants foraging or looking for food at the same time in parallel, instead of one ant with a large brain and counter. And also the other, it depends on the availability of food in the environment. So here, for example, we see that the more food you have, you can have larger colonies, and the brain size per ant can be smaller. And even here, you can see like the total brain volume of the whole colony normalized by the food availability, even this goes down. So you can think the more food there is, of course, you can hold larger brains because it's this expensive brain theory. More food, you can have larger brains, but still you can be like you can think you can be still stupider and stupider, even even if you normalize by food availability as food goes up. Okay, so this is maybe an argument why brains actually can grow smaller to save energy. Okay, there's another thing, idea why brains might be smaller, because maybe complex individuals are difficult to coordinate, right? So we have these huge groups of thousands, tens of thousands, even hundreds of thousands of ants, and you want to coordinate them all. So it's good if everybody follows the same simple rules, right? On the road, we have very, very simple rules, much simpler than we have on the sidewalk and much simpler than we have in this room, just because we want to get a large number of vehicles coordinated. So maybe again, we want to have smaller brains. So I'll come back to this later. And now I'll talk a little bit about the interactions of the. So of course, there's also changes to the interactions. And ants have evolved a very rich vocabulary. So of course, also other social insects as well. When I say ants, that's just my. So it goes from very simple interactions, like the interaction we see here. This ant is coming into the nest, she's just bumping into the other ant, and just this kind of, it's called an alerting interaction. The other ant knows something is happening, she has no idea what, but now she starts moving as well. Then you have ants use all their senses to interact, so they can use the vibrations. These are the leaf cutter ants, they feel the vibrations on the tree, on the branches of the tree, and they know how to navigate and where ants are cutting leaves, where they're not cutting leaves. And you have not really visible. They also communicate by vision, so they can do all kinds of displays. And actually, these displays are often visualizations of behaviors that were once real behaviors, and now they become kind of symbolic. For example, we saw before this trophylactic interaction, and ant is offering food. For example, display we see here, the ant is pretending to offer food. She's doing the same movement. She's not really going through everything. The other ants are not receiving food, but they understand that there is food, and then they go and follow her to the food source. It's called ritualization. That's the way it may have evolved, this interaction. It appears to have evolved. And of course, there's the chemical world of the ants. So it's much richer than the pheromones are much richer than most solitary insects. And of course, there are the parts of the brain that have to visit them. And the antenna lobes that have to process it are also larger, and they can make about in one species they can make about 150 different pheromones, which is quite amazing. And they can leave them in different places, so they get different communication. They can leave them on the floors, to make the trails. They can spray them, so everybody hears your message. Or you can give them really personally, so you rub the pheromone on your forehead, and then two ants meet, they antenate each other. And this is a personal, so of course, it's a very different language from ours. It's not a sequential language, but it's very rich. It has 150 letters. By the way, we have no idea why. Our models, we always try to simplify and simplify and simplify to explain something. And here we have the ants have 150 letters in their alphabet. I think nobody has any idea why this is so, why they need so many. The most complex models people make have 2 letters, 3 letters.
Do we have efficient means of measuring which one we're using then?
Efficient is not the correct word, but yes.
And do they form these into words?
Into word, no, but into combinations. So you
Combination of letters.
yeah. So 150, you can think if everything was independent, you could have at least 2 to the 150 combinations. Okay, so that was the message, or how the messages are which messages are relayed, and then you have also the interaction network over which these messages are relayed. And we know that connectivity is very, very important, right? For example, our brain, we attribute capabilities to the connectivity, which is we inherit it, and it's a very, very intricate connectivity, and without it, it would not be the brain. So we know that if you have smart connectivity, you can take even the simplest logic gates, you make any calculation you want, right? Or you can take very simplified neurons, and you can get a universal computing machine. So are the ants going in this way? Are they involving this kind of very intricate connectivities to be the smartest colony they could be? And here again, I come back to this. So there's a problem. When you have these autonomously moving insects that already communicate in central way, in given ways, and they have to move around. Each of them has to eat. Okay, it's not plausible that you will see them connecting. Like each of these will be neurites, and they will just be sitting in a web like this. And okay, so there are some constraints. These are insects, and they have to work with this. Okay, so they're not going to go probably in this direction. It doesn't seem to be. Not to say that there is zero structure, but structures are always very, 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 very light. So you can see here in this experiment, this is actually this feeding ants. So you see ants going out of the nest, and they will feed at the food source, and they come in and pass this food to other ants. So you can see how the food is flowing through the colony by a few foragers that go out. And now this is a later stage when more of the colony is full of food. And actually, when we analyze this, we see more and more that we can actually model what is happening pretty quantitatively and pretty well just by looking at random interactions. The ants don't really care. They don't really know who they're going to meet next. And even the interaction itself is kind of random. Two ants meet, food can pass either this way or that way, kind of 50%. How much each ant passes to the other is a random variable. Everything is very noisy. Who you meet, how much, what is the interaction? Very, very noisy. It still explains quite well what the ants do here, at least in this simple case. And if this is the case, that the structures are very loose, then the question, okay, so you cannot build, we know that if you have a, like this logical network, logical gate network, you can make any computation. But now the question, okay, if you have this very loose structure, what are the limitations? Maybe you still can make any computation, maybe not. Okay, so this is it's not an easy question, so this becomes a question in distributed computing actually. And usually if you go to distributed computing person and you ask him this question and you give him, okay, please take these autonomously moving agents that meet randomly and please compute this and that for me, he will come up with a solution. And usually when he comes up with a solution, and it comes back to me and tells me, I will feel cheated. There's always, they have these very cheats, a lot of kind of cheats like synchronicity or whatever. So you always feel cheated. No, but that's the answer. I'm surely not doing this. So with Amos Coleman, distributed computers to work a lot together, we try to remove all possibilities of these cheats. And I'll describe it here. So we looked at this very simple question. So the question is even not to compute anything. The question is, I have a number in my head. It's either 1 or 0. And now we walk around in the room, and then we meet in pairs. And then in the pair, somebody tells somebody the number. And the question is, can we come to a situation where at least 2/3 of the people know my number? So just very simple rumor spread. It's a very basic component and what we were able to show that if you have perfect communication, of course you can do it. Okay, so I just pass it to people, I tell them 1, and they tell the other person 1, and just very quickly in logarithmic time manipulation, everybody will know the number 1. So very quickly also. But now if we limit the communication in a way that you can trust everything, but not 100%, even 99%. So when I tell you 1, you hear 1 with 99%, but then 1% you hear 0. And you know that 99% this was me that told you this, but you think maybe actually it was him that told you, etc. So you have just slight possibilities for error. And if this is the case, there's no way, so we can actually prove, there's no way, okay, so no matter how smart the people are, how much memory they have, anything, there's no way to pass the rumor. Actually, the population is large enough, you don't have a chance, okay? So here, the only chance you have is to do it very slow. So I'm the only one that goes around and tells other people the rumor. Then high percent everybody will know, but then it's super slow. Like this is a huge huge increase in time. Okay, so actually we expect, so this is a very simple example, and the communication here is very limited. You can't be sure of anything, and it's not to say that each element never can pass a rumor. There are ways to go around this, but we can try to understand how the ants go around it. But just to say here that this kind of a structure that is imposed by the fact that you are actually wasps walking around, insects walking around, it has a limitation. You cannot do too much with these kinds of networks. Okay? Here it's not. You can't even pass a rumor. Okay, so here we see like one workaround. I actually won't describe too much the workaround, but just to show this noise and the randomness. This ant is coming outside into the arena. She found food, but the food, she can't take it, so she tries for 3.5 minutes, and then she says, oh, I need some help. She goes back to recruit, and she tries to recruit quite a lot, as you see, but nobody comes out, actually. Okay, and then she has to come inside again, and only then she can recruit. So actually, we can see here that the number of ants in the experiment, as it grows, it becomes more and more difficult. Okay? At the beginning, she recruits more and more ants, but then actually it goes down. She recruits less ants. Okay? Actually, we can attribute this to this noisy kind of communication, this random kind of communication, and this is what the solution of the ants to overcome this. So the solution was, okay, we're gonna respond, but only for small numbers of ants, and we're gonna give up a large number of ants, and this is the workaround for what I showed in the previous slide with the ants. Okay, but you see, it's very limited. It means they limited themselves in what they can do socially or collectively.
And that's independent of quality of the resource.
Yeah, well, it's a very good resource.
Right. So
this is the best. I mean, dead insect is the best resource for this. That was
assuming that the individual ant that's doing their recruiting is the only one. If it successfully convinces one of the other ants, does that ant start recruiting?
Yeah.
But you said it's like.
We can go back to it. Okay. We can go back to it because it's not meant to be more than a detail. Yeah, perhaps I'm going fast. I'm not sure. Yeah, so now let's try to look together about this. We have interacting individuals in the colony. So kind of try to connect the individual part and the interactions part. And again, we kind of go to the question that we asked before with this model. So for example, an ant colony, which is nicely sized. This is not a rare size. Each ant has about each ant has about 200, same kind of the number of neurons. Then together, you will have about 3 10 to the 10th neurons in this kind of ant colony. And we can kind of ask theoretically, just as a mind game, how is it best to deploy these neurons? So actually, this number of neurons is what you get in a chimpanzee. So this is in a nice big colony, not huge. You have as many neurons as a chimpanzee. And then you can kind of think, okay, where are the ants sitting in this? Can we explain this? So first, they actually can relax the need for large brains. So smallest insects have about less than 10,000 neurons. Maybe the ants should go in this direction and just be the smallest possible, have the smallest possible brain that we know for an insect. Or maybe they should somehow unite in this huge network, right, and make one huge brain. But again, this way is impossible. Okay, so they cannot increase too much. The largest insect's brains, I think, are around 1 million neurons. So the ant is somewhere in the middle. She's kind of stuck between these two things, between let's say 10,000 and 1 million neurons. And the question is this good enough for maintaining a colony? So first, as many people said here, brain size doesn't mean too much about the things you can do. Of course, it does mean something, but you can do a lot with small brains. Let's say this is the well-known example of the desert ant. which can navigate doing vector integration. If everybody knows this example,
no.
I can. So these ants. So this was done in the Saharan desert, somewhere where there's no features at all. There's nothing to go by except the flat sand and the sun. So the sun is the only feature. And what these ants can do, they go out to search for food, for dead insects. So they're very similar actually to the ants in the experiment I showed before. And they search for food in this manner. Okay, so they don't go in a straight line. Maybe they go in a way which is optimal for searching for food, which includes a lot of turns. And all this time, they keep a path integral of all they did in their head. So they count all the steps they did, including the angle, and they keep the vector, the homing vector, in their head. So a human can only dream to do something like this. We can't even go in a straight line and come back, I don't know, maybe one turn. And then here you can see when she finds the food, you can really see she turns and goes straight back to the nest. And if as she finds the food, she'll be moved here, she'll go straight back to here. So there's no landmarks guiding her, so it's just this vector in her head.
But that really is 10 meters.
Yeah, this is huge. It's huge. So this you can do with a small brain of a few 100,000 neurons. Another thing you can do with small brains, so maybe I put it here because it connects to some other talks that we had, and also because I'm very excited that we just brought these ants back from Australia a month ago, and hopefully soon to start working on them. So these are weaver ants that they bring leaves together on a tree. The leaves are still connected to the tree. They kind of construct this 3D puzzle of leaves to make a ball, which is what we're interested in. And then the next step is to hold the leaves in place. They come with the larva. The larva can make silk, and the larva in this, the pupa in this species are cocoonless, so they can donate this silk. And here it's donated to holding the leaves together. And you can see the adult ant is carrying the larva in her mouth and weaving, touching one side of the leaf, one leaf, and then the other leaf. You can see her kind of moving her hands from here to here, and back. It's a very cool behavior. Huh? Yeah, it's their own larva. Yeah, so it's a nice behavior. And actually, these Tullius, I think, I don't know if it occurs in other in insects that are not social insects. I think most examples are from social insects, like Tullius in insects, and this goes a little bit with this social brain idea. This evolved only in social insects. Maybe they're somewhat smarter. Okay, so ants. So first thing I want to say, okay, the brain of ants are small, but they can do a lot with this. So maybe it's going to help them to maintain these huge societies. And the second thing I want to say, which is important here, that in ant colonies, and I don't know about human colonies or neurons in the brain, I'm sure it's not like this. The individuals in the groups often face very similar goals. Okay, so here we see an individual which is carrying a piece of plastic, which we made smell like food to the nest. And here we see, I don't know, 100 individuals carrying a larger piece of plastic, which we made smell like food, to the nest. Very, very similar kind of behavior. Okay, it's just scaled up. Okay, it's not that here you have something completely new that the individual has no idea about. Okay, it's almost the same. And if you look at the behaviors that the ants do, this is often the case. Okay, when they search for food, they're just augmenting what the individual already needs to do and already does to some extent. Okay? And here, so we're going to see what evolved from this. So this is how it looks like. This is the cooperative transport, how the ants move these pieces together. And there's some things to say here. So first, you can see the coordination. You can see that this is kind of slanted. Why? Because the ants here are pulling, and the ants in their back are lifting. Okay? And this gives you cooperation, right? If everyone would pull or lift on will, it will just not move anywhere or move very slow. So you have this operation, and it's a very simple one. You can describe it by very simple rules. Okay, so again, like what I was trying to say before, when you have these collective algorithms, they're going to be limited, and you cannot go much beyond simple algorithms. And the rules here can be very simple. The rule can be if the food that we're all holding is coming towards me, because all the others are pushing it, or force of all others are moving it towards me, I'm just going to pull it as well. Just go with the flow. And if it's I'm holding and I feel that it's going away from me, I'm just going to lift. Okay, very, very simple rule. Don't need too many brains for this. Actually, we model this with just with magnetic spins, like just which have no intelligence whatsoever, and you can get this motion. And then we further found, okay, so this gets you moving. It doesn't get you home because you don't get the right direction. You just move. You just amplify whatever direction is already there. So how do you get home? So here the direction home is to the right, just like here. But these ants, because they're just going with the flow like this, they often make mistakes, and they're just now going with the wrong flow. And the good thing is, when you see here, all these ants are going to make a mistake. Now they're carrying the Cheerio. So they're going up instead of right. And the good thing is that now comes this ant from the outside. She knows where to go. She's well, as we said before, ants are very good navigators. She attaches to the Cheerio. And now she's able to really correct everybody. And even though there's 10 times more ants than her here, and they're all applying forces, she's able to divert the motion to the right, to the correct direction. Okay, so two things I want to say here is first, this ant is the way the direction in which she pulls is not some random direction. It has to do with her high navigational capabilities. It can be towards home. It can be towards a door that's on the other side from home, and that she knows her way around. And she applies this knowledge and injects it directly to the group scale. So she's very important here. Another thing about her, after 10 seconds after she attached, she will also kind of lose herself. For example, when you carry something big, you can no longer do this vector integration because you're being pushed around. She will step down from her leadership role. Okay, so she took initiative when she knew something. When she stops to have an informational edge, she stops. She becomes a regular ant. So that's another thing I want to say. And the third thing I want to say is how come she was able to win over all these ants? Because there's more than her, and then you would think that she would contribute just 1/10 of the power and not make really a sharp turn to the right. And then the reason is, again, we can explain it by this social algorithm. The ants are what I told you, pull if it's coming towards them, and lift if it's going away from them. So actually, the only thing you need to explain is to say that they do this probabilistically. Okay, so they do it small 80% of the time, but 20% of the time they just do nonsense. So this injects some noise into the system, and this noise, we can think the ants are not completely conformist. They don't do always what the group tells them, 80% of the time. And this little bit of noise is what lets this leader ant take control and move them. And actually, this noise, we can really model it. We can really, in this, I told you we liken them to spins. We can really model it as temperature there, and we can show that the ants are sitting near the phase transition, and near the phase transition, materials have high susceptibility to these kind of external influences. So again, the ants are doing something very simple. Okay, it's smart. They're cooperating and not fully, etc. It's smart, but very simple. And it's meant to take the knowledge of the single ant. She has good knowledge, but she doesn't have enough power in her muscles to move it. So it amplifies her power, so she can get something large moving. So now about the evolution of this. So the evolution seems to be, I don't know if this is true, but you can just hypothesize. You can hypothesize quite a simple evolutionary path. So how come the ants are standing around the object like this? So they do something with these ants, many other species do a very similar thing when they find prey. Actually, usually they carry prey and not the Cheerios in nature. They just go around the prey. Each ant gets one leg, and they just pull backwards all the legs, all the antenna of this arthropod. Eagle spreading it. And that's the way you capture it, but it's already puts them in the stride, the formation in which they're going to carry. So that's one thing. It may have evolved from this, maybe quite simple because you really do it on trade. When you catch it, and then the leader ants just behave as solitary animals. To become a leader, you don't have to do anything special. You just have to imagine there's no one else there. Because you know best now. There's no one else there. I don't care. I know where to go. The leader ant doesn't have to do anything new that was not there before cooperative transport. Just has to grab onto the object and pull towards home. That's it. And of course, but the leader has to be a capable navigator. And they are like any other insect. And that's what you need to evolve, is this capability for other ants and also the leader itself to let go. Okay, so this is something that is needed to evolve. When you're carrying something, you want to go with the flow sometimes and not try to carry it home or where you think home is. So this is really maybe the difficult step in this in evolving this cooperative transport. So again, we see like here we have this golden thing that the ant can do, single ant can do. She can navigate very well, and the population is just going to build upon this an extra floor, maybe a smaller floor, as I'm trying to present here. Individuality is very important. The capabilities of the individual are very important. You just build an extra floor, which is going to help them do it as a group. It's non-negligible, but it's still I think it's still individuality is for sure not lost here. It's very, very important. So this work on more complex situations. So of course there's different problems when you have this single ant and the group. I said the ant knows where to go, but the ant has a very different point of view on the world than what the group of ants may need. Okay, so this is this notion of Umwelt. We all see the world differently, different species, I mean, not even all of us, and we have to react, and the animal has to react to what its senses give it. It can't react to other things. Okay, so as humans, so this was the notion given by von Uxel, and this is how he imagined himself. How he reported that he sees his street, and how he imagined the housefly would see the same street. And of course, if the housefly has this information, it can't do everything that von Uxel can do. So this is this notion of a self-centered world. And when you have these two length scales, and when you say that the small ant is the one responsible for the navigation of the whole group, so you can ask this question: how well does the Umwelt of an ant coincide with the requirements of the colony? Okay, so it may not coincide. For example, you can see in this example, which was a natural unstaged actually, an eucalyptus leaf and a pumpkin seed, and the ants are carrying this pumpkin seed home, and single ants just go freely under the eucalyptus leaf, but the pumpkin seed cannot. So we see that somehow here the ants are trying, single ants are trying to guide the group from here, but this seems to be unhelpful. Okay, so this is something that the group has to solve. Okay, so we can't have everything from the ant. We can't just have very smart ants that know how to navigate and they will solve all problems. There is something to do for the group, and actually this is done. So I'm not showing it for the sake of time, but this algorithm of the group that I showed before solved this, and very quickly they will go around. So yeah, usually I show these slides. I should maybe. And another one is information conflict. So here you have this individual ants that really know where to go, but they may be conflicted in their information. So here we have this kind of a setup where we have a long corridor. So here you see long corridors and a door on each side, and the nest is actually on the top. Okay, so some ants from the nest going from the left, and some are going from the right, and we want to see what the group does. How will it resolve this conflict? So here, ants coming only from the left, and if they come in only from the left, this large objects that the ants are carrying will linger near this left side. Okay, sometimes it will go away, but then come back. Okay, so you have an exponential distribution here. But if we open the right side as well, what happens is that not one side wins. Even if one side has more ants than the others, we always get the ants going to both sides, trying both sides. So actually, both sides are blocked. The ants can go in, but the food cannot go out. So you can follow it for a long time. And you can see here, they just go back and forth, back and forth. It depends on the size of the object. And they try all solutions. Try for a while. If it fails, they try the other one. If it fails, they go back and back and back. So there's no absolute force for the majority here. They have not, this algorithm that I just told you in the beginning is the very same algorithm. That's very well. So finally, to finish this individual versus group, how much of the let's say colony cognition comes from individuals, how much is added by the group? I kind of try to stretch to stress the importance of the individuality, and I think in many examples this is correct. Like I looked over many examples, and actually not only in ants. I've studied the immune system before, etc. I think it's also holds there. So often I think the case will be like I tried to describe here. A lot of the weight falls on the shoulders of the individuals. Why? Because they can do it already. The colony has to face similar tasks to what individuals faced a long time ago. But there also can be other extremes. It's not to say that this is the only case. So one is here is the ants that go and this foraging in the desert ants. It's a lone endeavor. Each ant does it alone. The other ants in the colony are almost not important. Okay, so at least for this behavior, 100% of the weight falls on the shoulders of individuals, and she does this vector summation, etc. And there's also other examples on the other extreme case. For example, the termite mound. And the termite mound is very impressive. We also saw pictures in some with the people standing here. So it's a very impressive structure. It has a very stereotypical cone-like shape, and also inside there are floors and there are staircases between the floors. And actually there are models to show how this is formed, where the termites are just taking as very simple particles which interact with so we have the termite particles, and we have the mud particles and pheromone particles. And you can just show how all these together, the interaction, these pattern information, which is the termite mound, just like the pattern formation on the structure of the zebra. Okay, so here actually in these kind of models, as we understand now, maybe the individuality of the insects has a lesser role. Okay, so we have this whole spectrum. I think that the most of the behaviors are here. I may be wrong, but just to say that there's this whole spectrum of group organizations. And should I have a thank you slide here? Okay. So just want to thank the people in my lab. One of them is sitting here. We all.
Okay, so lunch is coming up, but we have time for a few questions. So, just vision one.
Did anyone look at the possible correlation between colony size and the relative size of the brain?
Yeah. Yeah, there's not too much correlation. If you go in specific area, specific environments, and then you can try to do it, and then sometimes you see that it becomes smaller. But the constraints you have to put on yourself to see it are a bit large, so it's not a clear correlation. For example, the ant from Australia I just brought back, they have a nest of 1 million ants, and they're quite large ants with large brains.
Well, Dan has also a question for you. Dan, do you ask?
Yes, wonderful talk. I have a question that arises out of your discussion of Umwelt. Hi. You showed a group of ants, you had a little video of a group of ants trying to move a leaf past a barrier, and there was no way to solve the problem if you don't have a larger scale perspective. How did they solve the problem? How do you get a bunch of individuals to discover solutions to problems that require a higher level perspective? Right.
So so much of our experiments are now in this direction, so we know some of it. We don't know all of it, but in the case that I showed, we understand quite well. So actually, I didn't show, but the ants also during this process also leave pheromone marks on the ground. So it's a little bit like the second example I showed. They leave pheromone marks on the ground, and they mark, and individual ants that reach the object mark possible routes to bypass this barrier, and eventually the routes that ants lay will be checked by so even though most ants mark towards the inside the obstacle where you cannot pass, eventually they will also test the other bypassing routes and find a way out. So actually, it's a very simplistic very simplistic explanation. I can explain.
Right. So a follow-up, if you don't mind, are these bypassing routes present whether there's an obstacle or not? It's just that they don't use them except when there's an...
So usually they won't have time to form if there's no obstacle.
Okay, so the bypassing routes are
they are more rare to be late, and then if the object is thus moving without any interference, then ants won't come from the outside. Most of them do from the around. Also, just the interaction with the ants that search for the food, they hit the obstacle from the other side, and this helps. And this also causes them to come from around, right?
Okay, thank you.
And one more case in which you have a reduction in brain size is during domestication. Most domesticates have a smaller brain than the non-domesticates.
Okay.
And this is very, very interesting. And it is probably because they don't have to do all the difficult things that you have to do when you're in nature, your food is provided, and so on and so forth.
Right.
Now, I was wondering, when you have these ants that are doing things really, the whole is the sum of its parts, so to speak. You're just scaling up, but in a linear kind of way. And in cases when you're not scaling up in a linear kind of way. So if you're comparing these two groups, do you see a difference in brain size?
Yeah. So empirically, I don't know. Empirically, I cannot tell you. This toy model that I showed before, then yeah, you put in all these things and you get what you expect. Smaller brain, you can even get a differentiation to two casts. One large brain cast that does the searching, and one small brain cast that does the collecting. You do see sometimes in ants, like soldier ants, they need very strong mandibles, and then they need the room with the head. It's more important to put muscle there than brain.
Yeah.
So then those might have smaller brains, for example. But I don't know if any good clean studies that will show these kind of things.
Do you ever see the division of labor outside of those insects that have a reproductive division of labor? So do you see a non-reproductive division of labor in it?
Yeah,
without there also being a reproductive division of labor?
Yeah, without there being there's always a reproductive division of labor.
But you mentioned some ants, some colonies, they're not social, I guess. So I'm wondering the extent to which ant colonies participate as units of selection.
Yeah.
And whether you ever see current group level adaptations in the absence of evidence of a reproductive division of labor.
Yeah. I'm sure that the answer is yes. So there is this species of ants that are now becoming more and more popular because it's maybe one or one out of two species in the world that you can do genetic manipulation on, and it's this kind of a very strange species that all ants reproduce. And sorry, I'm not sure. There is division of labor. Yeah. So some of them, for example, will protect the brood, while others travel around more. So there is division of labor, and even starts at very, very small colony size. I think down to maybe 6 ants or 10 ants, even less than 10. You already start to see this non-reproductive division of labor. So tiny sizes. That's a paper from 2 years ago.
Yeah, I want to ask what happens if you have two individuals that are good navigators or informers, but they have different opinion about where to go.
Yeah.
Does this create kind of a really physical conflict?
Yeah. So that's I showed this slide where we have a corridor. So you can think of this corridor, and you let some people go out coming from here and some from there, and we have to take out something big. This air conditioning doesn't pass through the doors. So we created this specifically, and then we even had more individual coming from this door than that door. We thought actually what would happen if you have more here than here. So if you have the same, okay, maybe they somehow divide the time, but if you have more here than here, it would be very difficult. You get stuck there, so it would be very difficult to reach the other side. We actually made them very, very far away as far as we could to make it more and more difficult to reach the other side. And once we see that what happens here is kind of a friendly conflict, whatever we did, they still always reach the other side. Okay, so they spend more time near the door where there's more ants coming in, but once they start going to the other side, often they will make it all the way through. Okay, so this happens from physical interactions. When the load is moving in this direction, it's easier for there will be more power for a leader coming from this side, where it's already going. When the leader from the other side will have lesser power.
Power is a function of the number of the leaders.
No, more power as a function of force. Like if I want to change that, it's easier to add force than to change the direction of something by 180 degrees. Yeah.
If the leader knows better,
yeah,
more force.
I don't know. I hope to know soon. Yeah, so I don't know. In our model, you don't need this. So
yeah. The background of my question is whether you have there is a combination of function and communication.
Yeah.
See, the signal, the leader is also signaling. It's not just pushing. He's giving a signal to the other. I know where to go. Please help me. Okay, or something like this.
Yeah.
But the idea is that he can just signal make a conventional signal.
Yes.
Like go this, but he can pull. If you pull in relation to his confidence and his knowledge, then you have a system of constantly signaling to arbitrate between possible uncertainties, despite that there is no conflict of genetic conflict.
Yeah. So we didn't measure single ant forces. We're on the way to do it. Since we have now these particles that also act as force meters, and it's not easy. They're tiny ants. But our models work quite well in explaining very quantitatively what happens. They don't have this. So and they still reproduce the results quite well. We don't need this change in force, and maybe it's again. I think maybe it's important because often, as I said, the minority is giving power, and I think the minority is where the minority is coming from. Actually, they are less sure of themselves, and it took a harder way, and it could be that the minority. Now I'm just rationalizing, but it could be that the minority is correct because of this Umwelt issue. You cannot ignore minorities, and then maybe it's better not to have this this extra. So you have majority, and they're also more strength, put more strength, so it will reduce the effect of minority. I think here, what I see in this behavior is that the minorities are being heard more than the relative fraction.
Okay.
Okay. That's lunch. I think 10 to 2. 10 to 3. 2:50.
לפי הלו"ז.
הכל בסדר, התכנסנו חזרה
Hey, Dan.
Hi.
So we are leaving for lunch, and we will be back in 1 hour and 20 minutes.
I will try to be here. Thank you.
Okay, welcome. Bye.
Bye.